In this lecture, I'm going to be talking about Newton's method. So some motivation for Newton's method comes from the problem of having to find roots of more complicated equations. So if we consider these couple of examples, how would we go about solving these equations? We've got 1/3 x cubed plus 1/2 x squared plus 3 equals 0, x to the 6th minus x to the 5th plus x plus 10 is 0, and 3 cosine x equals x plus 1. So with a cubic, there are formulas for the solutions to a general cubic equation, but they're really complicated. And there are in fact no formulas in the case of these second two examples. There's no formulas for polynomials of degree greater than 5 or for these sort of non-algebraic kinds of equations. We don't have a polynomial, we have some kind of trig thing equal to a polynomial. So how can we go about finding these roots? Well, Newton's method is a method for approximating the roots. So we want to talk a little bit about how this method works. And the reason that this method falls in this chapter is because it's an application of derivatives, in particular the application that we've talked about earlier that uses the derivative to get a linear approximation to our curve. So Newton's method makes use of this linear approximation. So if we consider a curve, maybe it looks something like this. Let's say this is our function f, and it has a place here where it crosses the x-axis, and that's the root that we're interested in finding, but it's really hard for us to solve that algebraically. So we take some value that's close to our root, we call that x1, and maybe that value is easy to evaluate in here. We pick up some nice value, and then we talk about its tangent line to the curve. So I'm going to draw the tangent line here. And then we see where that tangent line intersects the x-axis, and we call that x2. So if I think about the equation here of my tangent line to the curve at x1, this point is x1 comma f of x1. Okay, and the slope of that line would be f prime of x1. So I could talk about this line L having equation y minus f of x1 equals f prime of x1 times x minus x1. Okay. Then I'm talking about being interested in this point x2 where this line crosses my x-axis. So if this is my line, the point x2 comma 0 is on the line L. The way we've labeled this. So I can say that, let's see, 0 minus f of x1, plugging in 0 for y and x2 for x, is equal to f prime of x1 times x2 minus x1. So I can solve this equation for x2. So I have negative f of x1 equals f prime of x1 x2 minus f prime of x1 times x1. Okay, so we add this piece over here, so I have f prime of x1 x1 minus f of x1, and then divide both sides by this f prime of x1. And so this gives me what x2 is in terms of my function at x1 and my derivative at x1. So let me just simplify this a little bit. So I've got x2 is, let's see, if I break this up into two pieces, this would be f prime of x1 times x1 all over f prime of x1. So that'll just give me x1 minus f of x1 over f prime of x1. Okay, and I could then do this process again. Now I have this new closer approximation to r, that is x2. So x1 is a first approximation of my root r, and x2 is my second approximation. But then I can talk about finding the equation of the tangent line to the graph at x2, and then solving for some x3. That would be an even better approximation. So this is an iterative process, and this process of root finding that uses getting better and better approximations each time, this Newton's method algorithm in particular, is often used by your calculator when it's trying to solve for the roots using its built-in algorithm. So we're trying to kind of understand how various computer systems are approximating our roots for us, and also practice applying this linear approximation to this particular context. So let's look at what the rule now says in general, using what we now know about with our tangent lines. So if we keep repeating this process that we were doing on the previous slide, we find another tangent line, find a new root, we're going to obtain this sequence of approximations, x1, x2, x3, x4. And if we call our nth approximation xn, and if the derivative of xn is not 0, actually that's one thing. When we did this division here, we're assuming that our derivative was not 0. Okay. Then we get this general formula here for the nth plus 1th approximation. Xn plus 1 is equal to xn minus f of xn all over f prime of xn. So this is what we're going to use in our different Newton's method problems. So what I have here is a figure taken from the text that's showing sketches of these different tangent lines for better and better approximations. So we've got, x1 is here, then we've got our first tangent line, then that gives us a new point to start with, and then we sketch a new tangent line, and then that intersects with our x-axis and gives us yet another approximation, and we do the same thing until we come very close to the actual root. Okay, so what we're doing here is in fact a limit. We see that if xn is going to get closer and closer to this root as we take more and more steps in our approximation, then we have this sequence of approximations converging to r, and we can say that the limit as n goes to infinity of xn is equal to r. But sometimes this method doesn't work. We have to be very careful in what we choose to be our first approximation. So if you're working on an example and you've picked up a particular initial value for x1 and you're using this process and you're not getting closer to some value, then it's possible that Newton's method is going to fail and you'll need to go back and pick a different initial approximation to use. Okay, so let's take a look at this in the context of an example. So we want to work with this equation that I mentioned earlier. We're going to use x1 equals -3 as our initial approximation, and we want to find the third approximation. So here we're trying to find x3. The third approximation to the root of this equation here. So I've got a sketch of this particular cubic where f of x is equal to 1/3 x cubed plus 1/2 x squared plus 3. Okay, and so this equation represents where this graph crosses the x-axis. So -3 is this value just to the left of where it crosses, so it seems like that makes sense as a place to start. Okay, so we've got our function. Well, what do we need next? Well, in Newton's method, our formula also requires the derivative, so we're going to go ahead and compute f prime. So this example is made to work out a little bit nicely for us. So we have x squared plus x is our derivative. Now, using the formula from Newton's method, I know that my n plus 1th approximation is equal to xn minus the function at xn over the derivative at xn. So we're talking about, in this case, xn minus 1/3 xn cubed plus 1/2 xn squared plus 3 all over xn squared plus xn. So we just substituted xn into our function and the derivative. So I have this formula now. So to find x3 here, I'm going to have to find x2. So I've got x1 is equal to -3. So I need to find x2 next. Now x2 represents the case where n is being substituted with 1. So I have x2 is equal to x1 minus f of x1 over f prime of x1. So x1 is -3, so this is -3 minus, and now I'm plugging in -3 for x1 into my function, so I've got 1/3 -3 cubed plus 1/2 times -3 squared plus 3 all over -3 squared plus -3. Okay, And so you could do this arithmetic without a calculator. It would be just a little bit of work. But we will say that calculators are acceptable for doing the arithmetic here, but we have reduced something that we don't have a formula for to a case where we can just do some arithmetic basically with a four-function calculator. So this turns out to give us negative 2.75. So that's our second approximation to the root. So now I'm going to use this to find x3. So since I need a little bit of room, we'll go to the next slide. So we've got x1 is negative 3. We found x2 is negative 2.75. So now x3 is going to be x2 minus f of x2 over f prime of x2. So I'm going to have negative 2.75 minus f of negative 2.75. So that'll be 1/3 negative 2.75 cubed plus 1/2 negative 2.75 squared plus 3. Running out of a little bit of room here. All over our derivative. So this is going to be negative 2.75 squared plus negative 2.75. Okay. So now we evaluate this, doing a little bit of arithmetic, and we get negative 2.7186. So this is our third approximation. And if we kept doing this, we could get a better approximation to this actual root. But we just had to find the third approximation so we can stop at this point. Okay. So we want to look at one more example, but this gives us an idea of what the process is like. So here's our last example. We want to use this method to approximate the 100th root of 100 correct to 8 decimal places. So when we say that we want it correct to 8 decimal places, we mean we want approximations xn plus 1 and xn to agree to 8 decimal places. And when we get that to happen, we'll stop. Okay, so we're going to continue finding approximations until we get 2 successive approximations to be the same up to 8 decimal places. So what's new in this particular example is I don't have a function yet. I have a value that I need to approximate, but I'm going to have to get a function that this might be the solution to, and then talk about using Newton's method to find a root for that function. I'm also going to have to pick my initial value, so we'll see how that makes a difference here. So looking at this, I can notice that if I had the equation x to the 100 minus 100 equals 0, and I tried to solve that for x, I would have x to the 100 equals 100, and then I'd say, well, x must be the 100th root of 100. Okay, so this question of approximating this is the same as the question of finding the root of our example here, in particular the positive root, because we're not talking about finding negative the 100th root of 100. So I'm going to let f of x then be x to the 100 minus 100, so the problem really becomes, where does this function cross my x-axis? So I need to be careful when I'm picking my x1. Well, first let's go ahead. We know we're going to need the derivative, so we've got 100 x to the 99. And then I need to think, what should I pick for x1, for my first approximation? So you might think that you should pick 1 maybe as a first choice. I mean, that's a small integer. Certainly we know that 2 to the 100 is going to be way too big, much bigger than 100. 1 to the 100 is easy for me to evaluate. But if we use this choice, the convergence to r will be very slow. Because if we use x1 equals 1, we end up with the second approximation being 1.99, and then each subsequent approximation is just a little bit smaller. But we know that 1.99 is already way too big. So we want to pick an approximation that's a little bit maybe closer to 100 than 1 is. So if we start just trying a couple of things on the calculator, we might say that 1.2 to the 100 is approximately 8281797.4.52. So that's pretty big. What about 1.1? So if we try 1.1 to the 100, we get 13780.61234. Okay, so this seems better because if I do 0.9, sorry, these should be to the 100. We're just trying to get a good starting place. 0.9 to the 100 gives us something that's very, very small. We get 2.656 times 10 to the negative fifth approximately. So I'm going to say let's start with 1.1 for x1. But there's many other choices that you can make. This probably isn't even the best choice, but it'll give us an idea of the process. Using 1 as our initial choice is a very poor choice. 1.1 is better. There may be other choices that would allow you to go a little bit faster, but we're trying to start with something reasonable that will get us close to the true value in a reasonable number of steps. Note that when you're doing the root approximation on the calculator, you do something like first guess and second guess, trying to give it a value on either side. So you're giving it an initial value to run in its algorithm where it's trying to then estimate the root for you. Okay, so we're going to use this value, and I already have x4 here, so let's see how we can end up with getting to x4. So we're using x1 is 1.1. We said that f of x is going to be x to the 100 minus 100, and that f prime of x is going to be 100x to the 99. So our x2 needs to be x1 minus f of x1 over f prime of x1, which means x2 is 1.1 minus f of 1.1, so 1.1 to the 100 minus 100, all over 100 times 1.1 to the 99. So if we do this, we get 1.089079822. Okay, so that's big long decimal, but we don't know if that's close enough yet, so we have to do this process again. So with x3, I'm going to do x2 minus x2 to the 100 minus 100 over 100 x2 to the 99. So now I'm writing x2 instead of writing out this long decimal again. And here we get 1.078403357. Okay, so that definitely doesn't agree within 8 decimal places of the previous one, so I have to do it again. So x4 would come from doing x3 minus x3 to the 100 minus 100 all over 100 x3 to the 99, and then we get this value. So we have to keep doing this process until we get our 2 successive approximations matching to 8 decimal places. Okay. So we're going to continue this process, and since we know the formula we're following each time, I'm not going to write it out. And I was using a calculator to get these various things, and I was storing the previous number in there so I didn't have to retype it each time. So it looks like we're getting a little bit closer. We have these two have these the same, but they're not the same to 8 decimal places. Then we're getting 1.048 for the 7th approximation, 1.047. Okay, now we're starting to get a little bit more of a matchup, but they're still not the same to 8 decimal places, so we go again. So we have them correct within, looks like 6 decimal places, but that's not quite enough. So we one more time, and now these match. So now we can say that using Newton's method, the 100th root of 100 is approximately 1.047128548. Okay, So you've got just a couple of problems on WebAssign on this particular topic, and we're going to talk a little bit more about some of the nuances of Newton's method in class. Let me know if you have any questions.